Hello everyone. Let us continue the third part of today's class. Okay, we have finished this page. Okay, next let us see section 5.1, MIMO channels in line of sight geometry. Okay, here is footnote 1. Let us see. Footnote 1. This section is based on material in reference 34. Okay, let us see reference 34. Excuse me. Okay, reference 34 is a journal paper written by Gaspert et al. The title of the paper is Outdoor MIMO Wireless Channels, Models and Performance Prediction, which is published in IEEE Transactions on Communications in 2002. Okay, we begin this chapter by considering the case where the transmit and receive antenna arrays are within line of sight of each other and there is no scattering in the channel, as illustrated in figure 5.1. Okay, let us see figure 5.1. Okay. So figure 5.1 shows the line of sight MIMO geometry. Here is the transmitter array. The transmitter array has NT transmit antennas. Okay, and the distance between the first and the second antenna is equal to DT and so on. Okay, and this is the receiver array. The receiver array has NR receive antennas, and the distance between the first and the second antennas is DR. Okay, and so on. Okay, between the transmitter array and the receiver array, the distance is capital D. Okay, and this is the case transmit antenna. Okay, and this line denotes the moving direction of the electromagnetic wave. Okay, and this line denotes the wave front. Okay, what is wave front? Let us see the handout. Okay, page 8, problem 1. What is a wave front? Solution. In physics, the wave front of a time-varying wave field is the set or locus. Okay, we will introduce what is the meaning of locus later. Okay, of all points having the same phase. Okay. Okay, so next, problem 2. What is locus? Okay, solution. In geometry, a locus, plural, loci, Latin word for place, location, is a set of all points, commonly a line segment, a curve, or a surface, whose location satisfies or is determined by one or more specified conditions. Okay, let us go back to the handout. Oh, sorry, the slides. And theta k is the angle between the moving direction of this wave, electromagnetic wave, from the case transmit antenna to the receiver array and the horizontal line. Okay. So under this assumption, we seek a mathematical expression for H and a criterion that assures a high minimal capacity, despite the fact that scattering is normally assumed to be required to support spatial multiplexing. Okay, denote the channel response between the case transmit antenna and the receive array by HK. Okay, that is, the channel gain from this antenna to the receiver array is a vector HK, okay, which we call the signature vector associated with the case transmit antenna. So let me ask you a question. What is the dimension of HK? Okay, so because we need to list the channel gain between the case transmit antenna and the first receive antenna, and the channel gain okay, excuse me. The channel gain between the case transmit antenna and the second receive antenna, and so on to the NR's receive antenna. Okay, so in the vector HK, there are NR elements. Okay. We assume that the distance between the transmit and receive arrays is much larger than the dimension, okay, that is the size of either of the antenna arrays. Okay, so D is much larger than the size of the transmitter array, and D is also much larger than the size of the receiver array. Okay. Under this assumption, it is appropriate to model the received signal as a plane wave that arrives with an incidence angle equal to theta k. Okay, so theta k is the incidence angle of the plane wave from the case transmit antenna to the receiver array. Okay. Okay, the channel has three effects on the signal. First, the channel attenuates the signal by an amount equal to the free space loss. Secondly, the channel introduces a common phase shift due to the distance capital D. Thirdly, the channel introduces a relative phase shift between the receive antennas due to the angle of arrival. Okay, you can say angle of arrival as AOA, okay, which is the abbreviation of the angle of arrival. Okay, we denote the free space attenuation by alpha, okay, which is equal to 4 pi f capital D over C squared, okay, where f is the frequency of the electromagnetic wave and c is the speed of the light. Okay, why does free space attenuation equal to this equation? Okay, let us see the blackboard. Okay, again, because I do not have a blackboard, okay, so let me use the Microsoft Word instead. Okay, so let me see my handwritten handout. So please wait me for a second. Okay, it is chapter 5, page 11, problem 1. Okay. Prove that the free space attenuation is okay. Let me copy the equation. Okay, and paste here. Excuse me. Okay, it's alpha, okay, which is equal to 4 pi fd over c squared. Okay, let us see the solution. The radial wave from the transmitting antenna spread out in a spherical wave front. Okay. The amount of power passing through any sphere centered on the transmitting antenna is equal. The surface area of a sphere radius d, okay, is 4 pi d squared. Thus, the intensity or power intensity of the radiation in any particular direction from the antenna is inversely proportional to the square of distance. Okay, I is proportional to PT over 4 pi d squared. Okay, so this is equation 2. Okay, here PT is the transmit power. Excuse me. For an isotropic antenna which radiates equal power in all directions, the power density is evenly distributed over the surface of a sphere centered on the antenna. Okay, so I is equal to PT over 4 pi d squared. Okay. Okay, good. Okay, the amount of power the receiving antenna receives from this radiation field is, okay, PR is equal to A EFF I. Okay, where EFF should be, okay, non-italic. Okay, this is equation 4. Okay, where EFF denotes the word effective. Okay. Excuse me. The factor. Okay, this AEFF called the effective area. Okay, this should be read. Okay, because this is important. Or aperture. Okay, this should be read also, because this is also important. Of the receiving antenna, which has the units of area can be thought of as the amount of area perpendicular to the direction of the radial waves from which the receiving antenna captures energy. Okay, since the linear dimensions of an antenna scale with the wavelength lambda. Okay, the cross-sectional area of an antenna, and thus the aperture scales with the square of wavelength, okay, lambda square. The effective scales with the square of wavelength. The effective area. It is wrong. The effective area of an isotropic antenna. The derivation of this is beyond the scope of this course. Okay. So let us see. Okay, AEFF is equal to lambda. Okay, lambda square over 4 pi. Okay, and this is equation 5. 5. Okay, so combining equation 3 to equation 5, Okay, it should be n dash. Okay, n dash. Okay, good. For isotropic antennas. Okay, PR is equal to PT over 4. I can directly copy this here. Okay, PT over 4 pi d squared. Okay, and lambda squared over 4 pi. Okay, because according to equation 4, PR is equal to AEFFI, and AEFF is equal to lambda squared over 4 pi, and I is equal to PT over 4 pi d squared. Okay. Okay, so this is equation 6. Okay, the free space attenuation is, okay, alpha is equal to PT over PR is equal to let us see. Okay, 4 pi d squared lambda squared. So PT over PR is equal to 4 pi d squared 4 pi over lambda squared. Okay, so it is equal to this equation. Okay, 4 pi d. Oh no. 4 pi pi d over lambda. Okay, square. Okay, and is equal to, okay, this equation copy to here. Okay, and is equal to 4 pi FD over C. Okay, so this is equation 7. Okay, because a lambda is equal to C over F, okay, the wavelength is equal to the speed of the light over the frequency. Okay, so this completes the solution. Okay, insert a black square. Okay. Okay, finish. Okay, good. Okay, so let us go back to the slides. Okay, so we have proved that the free space attenuation is alpha is equal to 4 pi FD over C squared, and the common phase shift by phi, which is equal to 2 pi d over lambda. Okay, why does the common phase shift equal to 2 pi d over lambda? Okay, let us see the handout. Okay, let us see problem 2. Prove that the common phase shift is phi is equal to 2 pi d over lambda. Okay. Solution. This problem is left as an exercise for you. Okay, because I think this problem is very easy for you. Okay, let us go back to the slides. Excuse me. Okay, the relative phase shift at the Rth receive antenna from the Kth transmit antenna is phi r, which is equal to negative 2 pi times r minus 1 times sine theta k times dr over lambda. Okay, So why does the relative phase shift is equal to this equation? Okay, let us see the. Okay, it is 25 minutes. Okay, and we have complete this semester's classes. Okay, so I wish you have all the best in the final exam and the winter vacation. Goodbye.